All right, we'll see if that works. All right, howdy folks. Sorry, I had to reboot my laptop here. The Wi-Fi just randomly died. That's definitely a little weird here. So, all right, but so there were two bugs we found in our hash maps when we were working on the lab. So let me talk about those real quick here, and then we'll get into search trees today. We should be able to do sorting and selection on Thursday and be all caught back up. So we should be in pretty good shape moving on here. So there's a lot to search trees. We're not going to get super deep into them because that's a topic you'll pick up in data structures or algorithms analysis sort of course. But we're going to look at essentially what we would do to implement them and how they work performance-wise. We're not going to make them smart or balanced at any point here, so we're going to deal with some of the downsides of the performance that can get fixed later. All right, so for our hash maps, the first issue was when we were resizing here. The number of items needs to get set back to 0 because as we go add new items back in, it would increment the count again. So our count was off here when we were resizing items, and then when we were deleting items, we need to take it down by 1 for that number of items stored. So when we delete the item, we'll go and remove it here. Those two then ought to fix up all the issues that we were having with our internal storage. Oh no, and one last one here. This remove here, we need to remove from the bucket, not from the main storage. So three things. So remove from that internal bucket storage. Sorry, let me zoom in a little bit here. Remove from the bucket here, decrement the number of items, and then make sure we're resetting back to 0 when we resize. So this is important, whether or not we're resizing to go up or resizing to go down. So you could just repurpose this resize method and use a factor here. It's probably the easiest thing for the lab. Instead of *2 here, right, you can just pass what do you want to do. So for resizing up, you pass a 2. For resizing down, you pass like 0.5. The downside of that is when you multiply by 0.5, you could get a floating point number, which doesn't work for a length. So you have to be a little bit more careful or specifically cast that as an integer after you multiply the length. Yeah? It shouldn't be, but like if we did something wrong or if we did want to change this by like if we changed it from, hey, let's always start at 10 to start at a different capacity, and when we did like the prime number thing, then we run into all sorts of issues. So for now, we probably won't, but just to make sure in the future that we won't have issues, probably good to add that sort of thing. But it should be pretty functional here. All right, and then this was just kind of playing with that, making sure it did actually work, because we didn't actually test this on Thursday very well for deleting items. The syntax for deleting is really ugly. You'd say we'd want to delete from the crappy dictionary key of a small black coffee or something. I'm not fond of this delete syntax, but that's essentially how you get rid of that from the dictionary without adding some other sort of remove method. That's the delete item method that we've implemented here. So yeah, hopefully that didn't go too badly here. And then we want to look at our trees. So let's look at search trees. So we had done binary trees before, where we said you have a left child and a right child, and that was it. And then we could add in to the left, we could add in to the right, but we had no real pattern to how that happened. So what a search tree does is it says everything on the left must be smaller than my parent, and everything on the right must be larger than my parent. So it's adding a structure to it here. And let's just go, I think we got our code for trees here. I'll just go copy paste, it's probably easiest here. So we can go use one of our trees here. And let's see which one of these trees. So we did, the priority queue was an array-based tree. This is not necessarily going to be the best structure for us. It works out relatively well once we add some of the smarter stuff. but we don't have any of that smarter stuff. So let's work with a linked binary tree here. So, okay, so we got to copy from here on up. So linked binary tree inherits from binary tree, which inherits from tree. Okay, we'll grab all of those here. That ought to be enough to get us started here. And then, look, we'll even cite our source, because we're going to be good habit for that. Probably a space. There we go. Okay, so that's where we got all of our trees. Now, a binary search tree is going to behave differently because on this one we're saying, hey, let's add to the left of a position or add to the right of a position, add something as root. We don't actually do all of those operations here. So it's not necessarily maybe the correct base to use here because we're not going to allow some of those operations. So we'll just have an add here. So maybe is it better to just use a different one? Yeah, let's just do a binary tree here because we don't want all the other operations. Here we can do height, we can do depth is empty, root, positions, children. Okay, let's do those ones here. So we'll still use the node here, but we're going to change the linked binary tree to be a binary search tree. And we can still have positions, we can validate positions, we can make positions, we can get the root, we can get the parent, you can get the left, you can get the right, you can get the number of children, but we can't add a root, we can't add left, we can't add right. So we're going to remove those. There's no replacing. Deleting is totally different, so we're going to change that one as well. So we'll keep a couple of these functions here so that we can still kind of navigate the tree. But all we're going to do now is have a way to add values. So we're going to define an add method here that you're going to add some data to. And what's going to happen is we need to find out where it needs to go. And it's going to be this nice recursive function. Uh-oh, am I losing? No, we still got bits. Okay, it's the other computer. So if we don't have a root, it's easy. We become the root. Right? If root is none, then we can make a new node real quick and throw root there without too much trouble. So we check if self.root is none, then self.root equals a self. What's our class here? A node given the data, and then we don't have a parent, we don't have a left, we don't have a right. That was pretty easy. Okay, we're just the data here, but now we have a root. So we just can give it data, and then we can increase our number of items. I think we're counting our size, so self.size will go up by 1. So we'll add 1. If root is not none, well, now we need to see, should we go to the left or should we go to the right? Now, this here is going to happen all the time. So we actually, what we want to do is we want to have a recursive function that we can use. So otherwise, Hector, my friend, thank you so much for donating those bits to the Student Scholarship Fund over here at the University of Michigan Dearborn College of Engineering and Computer Science. You can't tell, but I got it all in one breath. There's the deep breath. Okay. So if we don't have a root, done, we're super easy. Nothing else to do here. Otherwise, what we need to do is we need to see, okay, do we need to go to the left or the right of a given position? So we need to see, so assuming we have a root, right, because root is not none, then we're going to have a helper method here. So we're going to define, we'll call self.add. We're going to add the data, and then to what position do we want to add it to? We're going to start with self-root. We can define self-root. And then our helper add method here is going to know that, okay, we always have a value here, the data and the position. So we need to go validate the position. So we'll have the node is self.validate the position. And then we can see, okay, is the data less than or greater than? Because that's going to determine where we're going to go. So if my data is less than the node.data, then it means I need to go on the left. right? Everything less than has to go to the left. Then to the left. And greater than to the right. So if I'm less than the node's data, then if the node.left is none, then easy. I'm going to add myself as the node left. Node.left equals self.node, given the data. Now, we know the parent is going to be the node, right, because it goes on the left. So its left child then will become a new node here if we're less than. If it's not none, right, else we need to recurse. We need to call self-add again, given, now this is self.make position of the node. No, I'm sorry, node.left. Node.left. So if the node doesn't have a left, we become the left. If it does have a left, well, we're going to recurse. Okay, we're less than, but you already have one. So we're going to recurse on that position and try and add ourselves then to that position, to your left. So it'll put us somewhere in the chain here. So if we were to have sort of like a picture of this, see if we can't draw this out real quick. So when we have nothing here, say we added like a 7. So 7 then has no parent, it has no left, and it has no right. We're going to add a 4. So you say, okay, node is not none, so we're going to call adding at this position of root. The position of root does not have a left, and we are less than, so we would add a left then with a 4. Okay, so now node has a left, 4 has a parent. Now if we wanted to add a 3, and say, okay, well, root is not none, so let's add at root. Adding a root says, okay, you're less than, do you have a left? Yes, you have a left. Okay, so recursively call add now from here. And say, okay, 4, are you less than or greater than? Well, you're less than, do you have a left? No, okay, so we're going to add it in as a left. If we're going to add a 5, 5 is less than 7, it would recursively go to the 4. 4 says, okay, you're greater than 4, so do you have a right? No, if you don't have a right, we add you in as a right. So a tricky part with the binary search tree is we're also essentially a set. You don't want to have duplicates because you can't be less than if you're the same. So we don't allow for duplicates. So it might be easier to maybe add this in more of the map style, where you're setting particular values rather than adding nodes. Not too concerned about that right now. I think this is easy enough to track. But we can look at that other syntax on Thursday if we need to. So if the node is not less than, then we'll say, okay, elif my data is greater than the node.data. We'll repeat this process on the right. So if node.right is none, then we'll set a right child, being a new node, given data, and the node is the parent. Okay, now you're a right child. Otherwise, we're going to try and add it to, recursively add to your node's right. So because this is this recursive call in nature, I don't care how deep the tree is. It'll just keep on going, trying to track where it needs to go, less than, greater than, less than, greater than, less than, greater than, as many levels down in this tree as it needs to. Now, I can also then have an else. So if you're not less than or you're not equal to, well, you already exist in the tree, right? Maybe we just raise a value error or something and say node, or I don't know, data, already in tree. And again, this is the sort of thing, if we had like a map style, you'd have a key and an associated value, we could go update the associated value. But for our purposes, that's enough for right now. We could try and track that on later. So just the two cases. If we don't have a root, great. Otherwise, let's go and add it. Oh, and then we do need, after we actually set a child, then we should increase that count, right? We should take our self.size +1 and self.size +1. The recursive calls, right? We need to wait till we actually set the new child here. For recursively calling, we shouldn't count it here as size. But we can go and add it. So this should be able to add a bunch of items. Now, what we don't guarantee here is that we're going to be in any sort of good form. If you take a binary search tree and you say, okay, add a 1, add a 2, add a 3, add a 4, add a 5, add a 6, add a 7, add an 8. Well, we have this linear chain here, essentially, and our add operation will take n operations, because it has to go dive down n levels to find where the next one goes. That's not an ideal form. So one of the things the book gets into that we're going to skip, and you can look at in a further algorithms class, is how do you essentially balance the tree? How do you keep it from being so lopsided on one side? And there's a couple of common strategies for that. There's AVL trees and there's red-black trees, which we're just not going to bother getting into, but there are ways that say, okay, if I have too many nodes over here, maybe I should shift the tree around and sort of rewrite it here then as a 4, 2, 3, 1, 6, 5, and 7. Right? If you can be in this sort of structure, right? When we talked about the priority queues, if you can be in a full structure or complete structure, we're able to store this more efficiently, and then everything happens in terms of log of n. Because each level has the next power of 2 number of items here, the most operations we have to do is to find which level you belong at, for like when we did upheaping and downheaping. Same idea. So if I've got 8 items in here, and I were to go add a new one here, well, I just need to say, okay, less than or greater than 3 times. If I have 16 items in here, it's less than or greater than 4 times. If I have 32 items, it's less than or greater than 5 times. At the worst case, to see which way you go. So by putting yourself in this tree form, we're able to get logarithmic performance if we're in a good structure, in a good form, which we're not guaranteeing. So worst case, we could be O of n in this sort of performance here. Right? Adding, you could go all the way down a chain of items here if we add them in a bad structure. Worst case. Best case, it's just O of 1, it's the, we just put one thing here. You're less than the first thing, and it doesn't have a left. But on average, we're going to try and get to this logarithmic of n average performance to say, okay, if we can maintain a relatively balanced structure, most of the time it'll be some sort of logarithmic power of your n number of items. So it's pretty good performance. So to find an item, right, we can see if we contain an item, right, contains some data, it's essentially the same process here, right? We're going to say, okay, is the node that data, right? If self.root is none, we'll just raise a, some sort of error, empty, I don't know. There's some sort of empty error, I forget what it is here, but that's fine. Otherwise, we're going to call a helper method, contains, given the data and a position. So we'll return self.contains, the data, and self.root. Try and find, starting at root here, and we're going to go recurse. So we can say, okay, so the position, the node is self.validate the position, and then if the data equals the node.data, we're going to return true. Otherwise, we're going to return, we're going to check recursively. So if the data then is less than node.data, we're going to return self.contains the position, the data at the position node.left. Sorry, go to the left. If you're looking for something that's less than, go left. And actually, we should check here. So we should say if node is none, return false. Right? When we go validate, if you don't have a position here, we go validate our position. If the node is none, then we get back a none. Right? So if I don't have a left here, when I go try and get the left here, it'll be none. Oh, sorry, that should be self.make position of the node's left. Node.left. So make a position out of your left. It could be none. I'm not even going to bother checking right now. And then if it is none, when I recurse, I'm going to return a false. And then otherwise, yeah, 1 and 0, GG, are true and false. So 0 is false, and anything other than 0 is true. Python's really fun. Essentially, everything is true or false. Anything can be used in an if statement, which makes coding stuff kind of difficult when you're first learning it. Because if you say if something and if you didn't actually do the right thing, it will still be true or false, which is kind of crazy. So if it's not equal to and it's not less than, it's got to be greater than. We can essentially save one little if statement here and go to the right. Right? It's implied that if data is greater than node.data or else or something in here, right? Some sort of check. This is just implied, because if we didn't return, then we'll get here anyway. So if it's none, false. If it matches, true. Otherwise, go left. Otherwise, go right. Right? And we're going to just search through that tree. If it's less than where it's my current node, go to the left. All right? Now left to right, left to right, left to right. Did I find it? And if I run out of nodes, like if I was less than and you didn't have a left, it's gone. It's invalid. So something fun with this that you'll see, add a new thing here. If we were to draw a tree like this, and we had, let's do 7 and 4 and 9 and 11, 10 and 12 and 2. Is this a binary search tree? Binary search tree. BST. No, it's not, because the 9 here is to the left of 7. It's invalid. So this tree, this subtree rooted at 4, is a binary search tree. Tree rooted at 7 is not a binary search tree, but this sort of thing wouldn't be allowed, right? When we go call add, if we had this structure, we said, hey, let's add a 9, we'd say, okay, 9 is greater than 7, go to the right. Oh, it's less than 11, go to the left. It's less than 10, go to the left. You have no left, you are the new left. 9. We'll put it in here. So because we're controlling how things are getting added, we're going to ensure it's in a common form. Now, one of the interview questions we used to ask people, I don't know if actually we still do or not. It's been a while since I helped out with any of the interviews, is we'd say, given a binary tree, tell me if it's a binary search tree or not. And that, in code, takes a second. And if you haven't done an algorithms class in quite a while, you're like, oh man, this hurts my head. But remember, we did traversals a while back. We looked at how we could traverse a tree. So an in-order traversal here would allow us to figure that out pretty quickly. Because in order says, okay, start with the root, then go left, print the data, go right. Right? So if we were to say, okay, let me put that back. I shouldn't have left my tree here. So if I had my tree here, right, if we say left, self, right. So starting at 7, we'd go left. So we're at 7, right? 7 with left, self, right. We're going to do the left. So we get to 4, we go left, self, right. When we get to 2, we do left, self, right. There is no left, so we print self. So we would print out a 2, essentially. Or return what do we do with we return it? We print it. So we're just printing it, sure. We print a 2. Okay, there is no left, we did the self, there is no right. Okay, this call comes off the stack. Now we did the left at 4, now we'll do self. Print 4, is there right? Nope, there's no right. Okay, done. So we did the left call for 7, now self, we print 7. Now go to the right. Now we're at 11, 11, left, self, right. 11 says, okay, go to the left first. So that's 10, left, self, right. 10 says, okay, go left first. That's a 9, left, self, right. 9 says, I have no left, print myself. I have no right. That one comes off the stack. 10 says, okay, I did my left. Now print myself, go to the right. It has no right. That one comes off the stack. 11 says, okay, I did my left, print self. 11, go to my right. Now we're at 12, left, self, right. 12 has no left, prints itself, has no right. Done. That one comes off the stack. 11 did the right, comes off the stack. 7 did the right, comes off the stack. We've went in order. So an in-order traversal of a tree can quickly see whether or not you're a binary search tree or not, because you always need to be less than the next thing, less than the next thing, less than the next thing, less than the next thing. If everything is less than in an in-order traversal, you're a binary search tree. That's a quick way to check. Right? If we had that 9 over here, and we did this order again, and we said, okay, let's go 7, left, self, right. That says 4, left, self, right. That says 2, left, self, right. We get the 2, did self, has no right. Come back to 4, we did left, we'll do self. Now do right. Right is 9, left, self, right. We'd get no left, we print self. There's no right, comes off the stack. 4 did the right, comes off the stack. We get to 7. And then we say, oh, uh-oh, that's a mismatch. We are not a binary search tree because we're out of order. So the traversals make more sense if you have trees in a structured order. So in a binary search tree, the in-order traversal gives you the correct way of traversing this. So we can make an iterator for our tree. Here, we can define a, what is it, iter here that will pretty much, let's see, do this. We're going to start with tree.root, and then if, I'm sorry, self.root, and then if self.left of the position is not none, we want, because we have to recurse here. Oh, that's not going to work quite right, is it? We don't want to print. Let's see. The in-order traversal. We want to go left. I think, yeah, we need another helper method here. So an in-order traversal. Okay, so I'll just copy the whole function again here then. But let's make this a helper function of self, 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 a couple more selves, sorry, self, self, and then data is just self dot and self dot. Is that going to do this for us? Self in order traversal. So position is not none. We'll start with root, and then we want to in order traversal starting in the left here. Then we want to eventually yield the position data. Then we keep on going. Is that going to work? We give it a position, self-left of a position, self-left, the make position. So we don't have a left though. I think we might get a no or a none here again. That's going to be ugly. So let's skip this part here. Let's not have a default here. So if position is none, we're just going to return. Just bail on that one. So if you go to the in-order traversal left and you don't have a left, we'll just return, come right back to where we were so we can yield that position data. So we're going to start with root then, and then we'll say for, is this going to work? Position, or I don't know, value in self.inorder traversal, given the root, self.root. Yield value. That might work. Is that going to work for us? Oh, too many blank lines. Okay. Value. Okay. So we'll try making a tree. So a binary search tree. Binary search tree. Sorry. Tree equals a binary search tree. Tree.add. Let's add. I don't know. We'll just add a bunch of numbers. Let's try them and do them in order. So we'll do a 7, and then tree.add a 4, tree.add a 10. What do we have here? Right, 7, 4, 11. Tree.add a 2, tree.add a 5. Oh no, we didn't have one over there. That's fine. We'll add it in. Let's skip that. So we had the 2. We don't have the 9, so we'll add a 10, a 9, and a 12. Tree.add a 10. Tree.add a 9. Tree.add a 12 here. Should get us that form here, and then we'll say for value in tree, print value. See if we can get those back out in order. Nope. Node has no attribute data. Node doesn't have data? Can we call it data? Yeah, node.data. Where are we getting that? Node, oh, date. It says date. It meant data there. Data. Did I do that? Okay, I did that right over there. Try that again. In-order traversal takes 2 arguments, but 3 were given. Oh, we don't need to give it self here again. That's right. So it's a bad typo. Bad copy paste. Okay, so we're not really iterating here. That's a position. Yield the value, position data. Oh, data in position is not a thing, right? Position has a method for data here, or a function for data. So we need to print the data, position.data, as the function call. Try that. All right, well, we get 7. It yielded 1. Why didn't it keep going? I don't know, let's put it in debug mode. We'll see what happens. Debug. Let's step into in a second here. We'll step into our code. We're in the iterator here. This is self, right? So we should have the root node, and root should have lefts and rights. Looking good so far. So we got 4, we got 11. Looking okay so far. So let's see what happens here. So we're going to do the Inorder Traversal. We'll make a position here with root. That's fine. Inorder Traversal. Okay, if position is none, we return. If left is not none. Oh, we're doing these if not nones here. Okay. We're already doing that there. We'll traverse at the left. Make a position with our left. Oh, it didn't. We missed a keyword here. That's what happened. So it did it, but it didn't do anything. We need to yield that one. Whatever we get back from that value. That might do it here, because we're going to give back whatever we get from the traversal of the left, which might be the data, or it might be a left here. Okay, so I think this is fine. We can probably get rid of some of these checks here then, because we're already checking if it's none. Skip it. It'll probably never be none then. Okay. We'll just say if it's not none, go left. Otherwise, do the data. If the right's not none, go right. Try that again. Okay. Not quite what we wanted. It yielded a generator object. That's not it. So it did the left, but the left was that one here. We have to do another loop for value in. So I get for not copying out of the book, I'm sorry. Yield the value. Is that it? For value in. Yield the value. Try that. There we go. Okay. Fine. Okay. So iterating over this one again, getting the value back out for everything on the left. So for everything on the left, yield that thing that's on the left. So the generator object was giving you an iterator essentially. So we're going to say for every value on the left, give me the value, which was just a recursive call here. For every value, then eventually we'll get back this position data, right? In all of those subcalls and subcalls and subcalls. So we're going to call it at 7. It says, okay, go left. Okay, we get to 4. It says, okay, go left. We get to 2. It has no left, so we finally yield the 2. Then we come back. So we can watch this call stack. It's kind of fun, actually, to watch the call stack. We run this in debug mode. I'll take the breakpoint out of there. So our Inorder Traversal. The current position here then is 7. That's the top node. That's the Inorder Traversal call here. Okay, and then we're going to step into, so now we're going to recurse into our Inorder Traversal. So now we have a second Inorder Traversal call where the position that we're looking at is 4. Right, so we went left. Then we're going to go again, we're going to step again. Let's just continue. Now another Inorder Traversal call where the position is 2. So we finally got all the way left. So we got all the way to the 2 here. Then it has no left, so now it's going to yield itself. So it's going to yield that 2, and it comes back. So now it's going to be yielded here in the call to the left. Where's my stepping? Did it run to the end? Uh-oh. Int object's not callable. Did I break? I must have clicked something in debug mode because it runs. I'm not sure what happened there. I think I broke debug mode. But it'll go all the way to the left to go here. So adding's pretty easy. I mean, ish. Easy-ish, right? And it's just left or right, left or right, left or right, left or right. Traversing it, again, not so bad. Go all the way left, left, self, all the way right. Or right and then repeat. Left, self, right. So it's always left, self, right, left, self, right. And that sort of recursive nature here. Removing an item is trickier. So if I were to say remove the 4 here, if you only have one child, it's easy. You just take that child and put it up here. Now the problem is if this one has children as well, if this one had children, it probably doesn't matter actually. So I'm just going to say, okay, let's take my only child, make it be me, and it will just stay the same if there's only one child. So, and if there's no children, it's easy, you can just remove it. So those two cases are pretty easy. So we'll look at remove first. We'll look at define remove the data. So first we have to go find it. So we need to find the position at which it is, so that I can then start looking at that node for the value. So the contains is fine, but it doesn't really tell me where it is here. So I want to maybe have a little helper method for get position for some data. So to get the position of a data here, we can have a I don't know what current position, and oh, that's fine. That's fine. We'll get the data. Yeah, from a position. So we'll say from a position. How about we call that current position? So we need to go see if we can find this particular data first. So we're going to say if. Or we're going to make the node, right? Node is self.validate the current position, and then if the data is equal to the node.data, we're going to return the current position. We found the position. Otherwise, if the data is less than the node data, we're going to return get position given the data and my current position dot, I don't know, is it self dot left of the current position. Current position, I don't know what that type of head is. So if it's less than, let's find the position starting with to the left of here. And then if the data is greater than, well, essentially the only thing that's left here, right, is going to return to the right. So if it's not equal and it's not less than, it's got to be greater than. Let's go to the right of the current position. Right? Eventually, we're going to return the position, or these might be none here. So we do need to check that if node is none, we're going to return none. So if I try and validate the position and you don't have one, it's none. There is no position here. So we need to first get the position. We'll say the position is self.getPosition of the data. And we're going to start with self.root. So find where it is in here, and then we can say if position is none, let's raise a value error, right? Data not in tree or something. Otherwise, now we're ready to check. So we can say if was it position, no, tree self dot number of children of the position is equal to 0. This is pretty easy. All we need to do is unlink it from the parent. Okay, so we can say the node is self.validate the position, right? And then we'll say node.parent So if node is equal to node.parent.left, then node.parent.left equals none. Right? Else if the node is equal to the node.parent.right, node.parent.right is none. Right, so if we have no children, we just set our parent, whether or not with the left or the right, to none. We take ourselves out of the loop. We'll say, okay, we're not here anymore. Let's remove ourselves. That's that case. If we have one child, then again, we're going to validate here. But now we don't say it's the left or right. Well, we need to say which child do we have. So if no, so we'll say the child is node.left, and if node.left is none, or I don't know, child is none, child equals node.right. So assume you're the left. Oh, if you don't have a left, you must be the right, because we know you have one child. Then instead of setting the left and right to none, we just set it to our child. So we set our parents left or our parents right, if that was us, to the child. Take us out of the loop. Right? And then we should probably also, I think, what is the thing we did when we validated? We said, wasn't there a check to see like if we pointed to ourself, if our parent was ourself? I think that's what we did to invalidate our node. We would say our node.parent equals node to invalidate or something. I feel like we did that before. I don't remember where that is right now, but that's what we would do. So we would link the parent to the child if we only have one child. Now, if we have two children, now we have a problem, right? So if I have, say I wanted to remove 2, well, what needs to go in its place? I can't put well, I could put a 1 here, or I could put the 3 here, right? It could be either a 1 or a 3. So we need to make a choice here of what's going to get replaced and how are we going to run this. So the easiest way of doing this is to go as far right as possible to say, okay, let me grab the next largest thing. So in this case, we're sort of out of numbers here. Let me change some of these real quick. So if we had, say this was 6 and 3 and 4 and 5, right? I could put a 1 here, that could work. But if 1 had a right child already, I can't just put the 1 here because it already has a right child. So what I need to do is I need to get the value out, and I need to get the next version. So I need to go right and then as far left as possible to see the very next position. So if there was a left here, I would go that way. And if there was a left there, I'd go that way until I find something that doesn't have another child. Right? If I'm going as far left as possible, right, we're going to find the next descendant, essentially. And we can put that one in. So in this case, we can just take the 4. If it didn't have any positions here, right, we'd be able to swap the 4 in. We could just take the 3 out, put the 4 in, have the 5 here, and this could work. Right? That's a 4, not a 9, sorry, 4. So say we wanted to remove the 11 here. Well, what value do I want to put in this place? Well, I need the next number in the sequence. I'm going to go right, and then as far left as possible. So I'd swap with the 12. Because I can put the 12 here. Remove that. So there's the sequence in which we need to go find the next descendant, or the next position, to go and grab it and put it in our place. We're going to swap it out. So it gets a little bit funky because once I go right and I'm going as far left as possible, I know that I will not have two children. Because if I go as far left as possible, it means there is no left here. Right? There's no left child there. So it can't have two children. So I don't need to run into this problem again. It might have one child, and that's okay. If it has children, I just bump the children up to its place with that same swap. Now that child becomes this one here, and I'm going to take its value. If it has no children, then easy. It's no problem here. So I need to go find the next value. So then my else here really is, this is two children, right? Two children. Is I need to find the next value. So the next value, that we want to find, I guess, because we know we have two children. So we're going to start at so we should say the next descendant. There's a term for it. I'm trying to remember what it is. The next, that's not how you spell descendant. Descendant? Descendant? I don't know. Sure. Will be my position's right, and then we need to keep recursing all the way down. So we're going to say my position's self.right of the position starts here. And then while the next descendant, while the self.left of the next descendant is not none, our next descendant becomes that left. All right, it doesn't like how I spell it. How do I spell it here? Rename. But tell me how to spell it. This one's an E. Is define descendant. Descendant. Okay, it is an A-N-T. A-N-T? A-N-T. I thought I had A-N-T before and I didn't like it. Okay, that's fine. So the next descendant, right, starting at the right and then all the way left. When that loop is done, it has no more lefts. Okay, so then we get the node is going to be self.validate the next descendant. Now I'm going to take the data and I'm going to swap it in with me. So we got the position here. So position has just returns the data. So I need to get the node out to actually change the data. So then this is the node to remove equals self.validate the position. Okay, so this is the next descendant node. There we go. Try and name these nicely here. So we'll get the node we're going to remove is us, and the next descendant node here. So we're going to take the data out of this one and just put it in my spot. We're going to say the node to remove dot data is equal to the next descendant node dot data. Put the data there. Then the next descendant node, we need to take it out of the loop. We'll say the next descendant node dot parent. Oops. Parent. Right, we're going to change the parent. Now this must be, could be, so if we ended up with, what do we have here? If we had 13 over here, its parent would be the right. It's not always going to be the parent's left. So we got to check real quick and see which one it is. It's probably going to be the left, but it might not be. That's okay, so we can check for it. So we'll say, okay, if the next descendant node dot parent dot left, we'll check for the right. If the right equals the next descendant node, right? So if we're the right child of our parent, in this case, then we need to swap our right child, because we know there is no left child. So we're going to say the next descendant parent's right becomes the next descendant's right. So if we're our parent's right child here, so if we're going to remove the 13, or sorry, if we're going to remove the 12, we'd be swapping with the 13. We're going to take out the 12, we'll put the 13 here, and then say, okay, your right is now 13's right, which is none. We'll cancel that one out. That's good, okay? If, say, we were removing 12, and this was 14, and we had a 13 over here, our next descendant would be 13, right? If 13 is the parent's left child, then the parent's left child becomes that one's right. But still, we'd swap out the 13s. We put the 13 here, and then say, okay, hey, parent, your child now is my right child, which is nothing. We're out of the loop. But if it was something there, like 13 and a half, we put 13 and a half there. So if we're not the left, then elif, we can do this, I guess. It's got to be the else here. That's just the other case. So our parent's left then is going to be equal our descendant's right. Next descendant's node's right. Oh, we need the node here. Sorry, next descendant's node. Assign. So if we're our parent's right child, then set the parent's right child to our right. If we're our parent's left child, set their left child to our right, because we know we don't have a left. Eventually, right, we should take our self.size. Oh goodness, did we return anything here? We never returned anything here. Good. So we'll take, how about up here then? We'll say self.number of items or size -1. So we should be able to remove something by finding, so this method here is getting kind of ugly here, I'm sorry. But it finds the next position to swap by finding the next child in order. Right, so let's look at that again. So if we had this, we had 4, and then we had a 5 over here, and then 5, oh, we need more numbers, don't we? If 5 had like 4.5, 4.5 here, that's that's ugly, sorry, 4.5. We'd be removing 4, we'd swap with 4.5. We'd go right and then all the way left, we put a 4.5 in here. Its parent becomes its right child, which is nothing. And we're still in tree form, binary search tree form. If we're to move 4.5, well, we're going to swap it with the 5 here. Its child becomes nothing, right? If it has only one descendant, it's a different case. We're not doing this whole nonsense thing. This only applies if we have 2 children. Make a little bit of sense what's happening here and how we decide which one to go. So no children, 1 child. Oh, we still need to invalidate these things here. That's probably fine. Well, we can worry about that later. So that's the next descendant's node is essentially getting invalidated. Oh, we should be setting these things. So then the that's right, the next descendant's right.parent needs to become our parent, right? Skipping ourselves out of the loop. And then the next descendant's right. Okay, so that one happens either way then, right? Regardless of which one it is. Nope, no, it doesn't. Right's parent. Yeah, because it's always our right. Because it's always our right node is getting pushed there to become the parent. But we might not have a right. So if the next descendant node right is not none, then we'll go and set the parent, right? Because if it is none, that's okay. We've set their right to a none, or their left to a none, which is okay. but we can't change the parent unless they're not none. All right, so we should try it. We should try it. So we were going to add a bunch of values. We should be able to traverse through it here. Now let's try and remove some values. So we'll say tree.remove, and let's remove, say, the, let's see, so we had, we put them back in order. Let's do another page here. So we did 7. Oh, on this page, So if we add a 7, that, dropping my pen here, that becomes the root. And then we add a 4, should come over here. We add an 11, should come over here. 11, can't write here, I'm sorry. Add a 2 should come over here. A 10 should come over here. A 9 should come over here. And a 12 should go over here. So which one should we remove? Should we try removing the 11? And then see if the 12 goes in its place? So let's remove the 11. Tree.remove the 11. And let's print all of them again and make sure we didn't get any weird hanging things. Seems like I removed the 11, still printed out in order. I think that's a good sign because our traversal would probably break if we broke something. Let's try for fun removing the 7, remove the root node. So if we remove the 11, right, we're going to swap that with the 12. If we remove the 7, what do we expect to have swap with it? The 9, yeah, we go right and then all the way left. So we swap with the 9. That becomes null. Now everything to the right is still larger. Now this is why that's so important, right? Because the binary search tree rule has to apply. You have to take the very next number, otherwise not everything is going to be larger. So you have to find the smallest thing on your right to swap with. Okay, so we should be able to remove that and be in OK shape. We'll try it here. Tree.remove the 7. So we'll remove the 11 and the 7. 2, 4, 9, 10, 12. It seems like it's working okay. So again, our tree doesn't guarantee that this works well. So contains, you know, this is worst case, a big chain here is O of n. Because we have a right child, 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 a right child. We put them in order and we get a big chain. Worst case. Best case, again, we don't really care, is O of 1. It's the first thing. It's the root node. That's why best case is generally pretty silly. We don't really care. But on average then, you know, if can be somewhat balanced, we'll get O of log n. O of log n. Right? Because we'll have every next level of the tree will double the number of items we have in the tree. So if we're mostly balanced, again, you don't have to be exactly balanced to still be relatively logarithmic. Like if we've got 10,000 items, it's okay if you have like 2 extra levels on one side and on the other side. It's not going to be the end of the world here. But it should be mostly logarithmic. My goodness. Now, if you remember a while back, we looked at if we had a sorted list, we could do a binary search of a sorted list, right? You start in the middle, you're too high or too low. That's exactly what's happening here. But it's not necessarily middle, but to the left is lower, to the right is larger. So we're cutting it essentially in half. And if we're assuming we're generally balanced, you'll have mostly halves as you go down each level of the tree. So removing, again, is still relatively quick, because even if we have to do all this nonsense where we have to go find every single descendant, it's still going level by level by level. It should still be logarithmic. So, you know, again, assuming average, if we can be somewhat balanced here, is average. So that's for contained, and then for adding, same thing, right? To add something, you might have to shift left, right, left, right, left, right, left, right till you find an open spot, but it should be relatively balanced. And again, we're not guaranteed here with this bad form here, but that's okay. It's just our basic binary search tree. What are we not implementing? Oh, the children. I thought we did that. Children positions. I don't know. It's fine. Not too concerned. I think we do most of them. So that's the basic binary search tree. Again, it doesn't automatically balance. That's the next best thing to do. But this gets us to being in binary search tree form for adding things, removing things, finding things, right? The same kind of operations. Now, if you wanted like a first or a last, we could still do that, right? First would be go all the way left, last would be go all the way right. We could give you those sorts of things, and then you could iterate over them. So we could give you a position of first if we wanted. So we could add in something that will give you the first position, or something that will give you the last position, and then we have these ways of saying we have right and left, which is not really ideal here. So what we want to add is next or before, right? What comes before this or what comes after this, before and after position. So to say what comes before position, right, it's going to be the left and then most right, right? If you say, okay, hey, what comes before the 9? Well, let's say we add a 5 in here. You're going to go left and then all the way right. So you're finding the preceding descendant, not the next descendant, right? What comes before 4? We'll go left and then all the way right. Well, it's the 2. So we could add those sort of operations in to find what comes next to let you traverse the tree like one at a time. Instead of doing here's the traversal iterator, I can say, hey, give a position, I'll tell you what comes next or what comes after, before and after. We could add in those methods if we wanted to give someone the way to sort of look at things one at a time. And it's not going to be all that helpful because you can't add from a position. In a binary search tree, you just add to the tree figures out where it goes. Versus when we had the linked tree, we could add from a given position, or add in a linked list, we could add from a given position and get really fast performance. We don't have control at that level because the tree is a sorted form. The tree keeps it in some sort of structured form here. But trees are a lot of fun. So our binary search tree. Okay, and look at that. I think we ended on time. And did we test it? We added things or removed things, unlike our heap or our hash map that we didn't test, and I had some bugs for lab. I think we added and removed things and it worked okay. I think. Right? I think that worked. All right, awesome. So I'll get this committed to GitHub. And then on Thursday, we'll pick up some basic sorting and selection here. Two quick sorting and selection methods. And then next week, we'll get into ethics. It's a quick little ethics chat, and we should have a lot of fun. So we have lab next week, and then lab the 19th will be an ethics lab. And no lab the week after that. I believe classes are done, and then we're the 28th. Again, I need to aim for about 4 o'clock or so. I've got a doctor's appointment at 2:30, and they're usually not quick. So I was hoping it'd be done in time, but just in case I don't want to have to reschedule, so we'll just plan for 4 p.m. for presentations. We'll all hop on the Zoom link. I wasn't planning to come to campus unless you folks wanted to come. Let me know. But that might be after 4 then. We just all hop on Zoom and present the final projects. Which we got to start that. It is April, so we need to start our final projects. We've got 5 minutes. Do you want to start it today, or do you want to wait till Thursday? Is anyone actually going to start today? What? Okay. Anyone online want to vote? If you want to talk about it now or wait till Thursday? Because that still gives you 1, 2, 3 whole weeks. Today? Okay. Yeah, we can talk about it today then. No problem. So let me add this in here. Final project. So that is April 28th, and we said 4 p.m. for this one here. And it's 30 points. So if you'd like to work in pairs on this, I would definitely recommend it. It's generally a better experience working with somebody else. You can collaborate, kind of talk through ideas. But it does add more work because you have to do the collaboration and coordination and figure out who's doing what and testing your stuff together. So whether or not you do it individually or in pairs, it's the same assignment because it works out to be about the same amount of work here. So we're going to build a Yahtzee game. So Yahtzee is, let me just find the Wikipedia link here, the game with dice. So you have 5 dice, and you get to roll them up to 3 times to try and get a bunch of different scores. So the Wikipedia link is not all that great. There's an online Yahtzee, which is maybe a little easier for looking it up here. Is Yahtzee online? No, not that one. This one, cardgames.io. I think this is the better one. Yep. So this one you can play against a computer. We're not going to play against a computer here. We're going to do a couple other things. This will show you kind of how the game works here. For the game is played. worry about the computer. So there's a couple stages of this here. So the first part is getting it so that we can play a single player game, essentially, because we want to be able to roll dice, and there's an upper scoring section and a lower scoring section. The upper scoring section, I guess this isn't too bad here, you score by the total of the dice with the number 1 on it. So if there's 3 dice with 1s, you'll score 3 points. The sum of the dice with the number 2 when you score 2s. If you have 3 2s, you'll score 6. 4 3s is 12. 1 3 is 3, 2 3s is 6. So the upper section is all just the total of the dice with that number. The lower section scores a little differently. For 3 of a kind, so any 3 numbers being the same, you'll get the sum of all of your dice. Any 4 numbers being the same, the sum of all of your dice. And then some fixed amounts here. If you have a full house, that's a 3 of a kind and 2 of a kind, it's 25 points. A small straight, 1 2 3 4, 2 3 4 5, 3 4 5 6, 30 points here. 40 points for a 5, or a large straight, 1 2 3 4 5, or 2 3 4 5 6. A Yahtzee is all 5 being the same, you get 50 points, and then chance is the sum of all your dice. Don't worry about the Yahtzee bonus, that's not worth it here. The Yahtzee bonus for now. Okay, we'll just say ignore it. We don't need to worry about it. Yahtzee bonus scoring. So we're going to have a way for them to play, but what we want to do here is we want to figure out a way to tell the user what is the best option. So just being able to play it is one step, and then we're going to add a simulator that helps the user pick the best option. So after I roll some dice, right, so you get 3 rolls of the dice for each turn before you have to score, and you can say, okay, I want to keep the 6s here and roll the other ones. All right, I didn't get any more 6s. Let me try again. Okay, so I got 3 6s, so I can score 18. And I'll get my 18 score. And then Bill goes, what we want to do is, for a given roll, we want to say, what is going to be the best optimal score? What could possibly maximize your score? So we need to go through and we need to simulate. Here was our, let's search trees. Oh, and the hash map fixes. That's in there. Let me do that one first. And then hash map fix. Hash map fix. Okay, we got both of those. So we want to look at what they have available to score and what their role is to see what will give them the best possible score next. So given the first roll of the dice and available, what is it, area, I don't know, scoring opportunities, we're going to essentially go and simulate all of the possible rolls and see what could happen. So what happens if I re-roll all of them? What happens if I save this one and re-roll the other one here? So all those possibilities here, which is not actually as many as you think here, because there are 6 sides on each die, and there's 5 dice. So all the different ways that it could happen is, what's that, 6 to the 5th, right? 6 different faces across 5 dice. So 6 times 6 times 6 times 6 times 6, right? So it's only 7,776 different ways that you could roll the dice. And now this is permutations, not combinations, right? So if I roll a 1, 2, 3, 4, 5 with my 5 dice, is that any different than if I rolled a 5, 4, 3, 2, 1? No, it's not really any different here. So this is total possibilities here, total permutations, not combinations. So it's not that many more things to try and roll, but then we also have, okay, let's save one of the dice and let's go roll 4 dice. So then we could also, 6 to the 4 is a possibility, or 6 to the 3 is a possibility, or 6 to the 2 is a possibility, or 6 just rolling one of the dice is a possibility. So we have all these different things we're going to try, given what my 5 dice are. Let me try rolling them and see what is going to give me the best score. And we say, okay, and it's all just based on what will give me the most points on that next roll. So figure out which, what is it, strategy, or which dice to roll will give the largest possible score. Does that make sense? So like if I rolled 5 1s, what's going to be the best possible score? Rolling all 5, rolling 4 of them, rolling 3 of them, rolling 2 of them, rolling 1 of them, rolling none of them. Rolling none of them is actually the right answer there because you already have a Yahtzee for 50 points. So any other roll, the odds of that happening are pretty low, right? So we need to come up with what a possible score is from there. So we can talk more about it on Thursday, but we need to start getting the rules set up in the game, and then we need to start thinking about how we can start simulating that to see a predicted value for a given roll. So what the value could be here. So you're going to have to find the best possible score outcome versus how often you got that score. So right, for all different possibilities here, is if I roll all 5 dice, if I roll 4 dice, roll 3 dice, roll 2 dice, roll 1 dice, roll just 1 die here, and then for each of the dice combinations, it's actually a lot that has to do here, right? Because rolling all 5 is pretty easy, but there's 5 different ways I could roll. No. For 5 combination 4, what is Wolfram Alpha? Wolfram Alpha. Wolfram Alpha is better at this sort of thing. So 5 combination 4. So there's 5 ways I can roll 4 dice, right? 5C4. Yeah, so 5. Yeah, so there's 5 different ways you could roll 4 dice. Each of those times you roll, you'll get 1,296 different possible outcomes. Right, so if I have a 1, 2, 3, 4, 5, if I keep the 1, then there's 1,296 different things that these other 4 dice come out to be. If I keep the 5, there's still 1,296 things these other 4 dice come out to be for each one of those. So there's a lot of different possibilities. So we need to find the best possible future value here. So we don't want to do this with math, right? What we want to do is just make Python just literally crunch through every possibility here. We want to simulate it, right? We don't want to have to figure out the math. The math for Yahtzee, what's it? Yahtzee odds, yeah. Calculate the expected value. I Googled this before. Here, is it? Hang on. I think this one was pretty good. Here, you can do this. Like it is predictable here, but what I want to show you is that in code we can simulate these sort of things and actually try them out rather than have to figure out all the math for it. And some things are even harder to figure out the math for than other things. And we can say, okay, here's what could happen in code. We can just put these out in a model and try it a bunch of times and see what happens. It's kind of fun. So like someone did a Monopoly game and they simulated the game of Monopoly to say, what is the most likely property to be landed on? And they ran the game of Monopoly like 10,000 times. And someone else did it with math. And it's like, I don't even know how you do the math for that. So I think simulating stuff is more fun. So that's what we're going to work on for our final project. So we'll turn in the URL. I don't have the classroom set up for you yet. I'll get that here. We'll go from there. Okay. Sorry, we're a little over time now, but we got talking about the project, and this is what we're working on for all of April. I'm skipping the last individual project. We were going to have a 4th one. It's just not in the cards right now. This one's more important, much more interesting than the other one anyway. So we'll have extra time in lab to work on this. Extra time throughout the week. As we get closer to the end, right, that last week of class is set aside just for this. If you folks want to meet, do screen sharing sessions or come in person, hang out, and figure it out from there. Okay? All right. Awesome. You folks online, take care. I will see you on Thursday.